What is seismic engineering for bridge building? Imagine a bridge standing tall and steady as the ground beneath it shakes violently. How do engineers make that happen? That's where seismic engineering for bridge building comes into play. This field focuses on designing bridges that can handle the forces from earthquakes, keeping them safe and functional when nature tests their strength. It's a vital part of infrastructure development, especially in regions prone to seismic activity. Seismic engineering combines knowledge from different areas like structural engineering, geotechnical engineering, seismology, and materials science. Engineers analyze how ground motion during an earthquake can cause strong forces on bridge parts like piers, decks, foundations, and bearings. The goal is to create designs that absorb, resist, or dissipate that energy without causing the bridge to collapse. One key part of this work is seismic hazard analysis. Engineers study geological and seismological data to estimate how intense ground shaking might be at a specific location. This helps determine the forces the bridge must withstand. They then use dynamic structural analysis to simulate how a bridge will respond during an earthquake, considering the complex behaviors of materials and connections. Modern seismic engineering also uses devices like isolation bearings and dampers. Isolation bearings allow controlled movement between the ground and the bridge, reducing the amount of motion transferred. Dampers act like shock absorbers, absorbing seismic energy and lessening vibrations. These devices are often installed on new bridges or added to existing ones during retrofitting. Designing for earthquakes isn't just about making bridges stronger. It's about performance-based design, which sets specific goals like preventing collapse during major quakes and limiting damage in moderate ones. This approach balances safety, cost, and usability. Another important aspect is soil structure interaction. The behavior of the soil beneath the bridge during an earthquake can greatly influence how the structure responds. Engineers evaluate risks like soil liquefaction, where saturated soil temporarily loses strength and settlement, which can destabilize foundations. Historically, early bridges often failed in earthquakes because they weren't designed with seismic forces in mind. Over time, advances in understanding ground motion, structural dynamics, and materials have led to innovations like base isolators and energy-dissipating devices. These have transformed how bridges are built and maintained in earthquake-prone areas. In practical terms, seismic engineering influences many aspects of bridge construction. Engineers select appropriate foundation types, reinforce critical components, and design flexible joints that can move without damage. They also incorporate seismic devices to reduce forces and evaluate existing bridges to improve their resilience. All these efforts ensure that bridges remain safe and reliable, even when the earth trembles. Seismic engineering plays a vital role in connecting communities and supporting urban growth, making sure that our infrastructure can face the unpredictable power of nature.